Welcome to our section on how to monitor and optimize operational resources in Azure SQL. Coming up, we will be discussing resource optimization for your databases created using either IaaS or PaaS services. This section is all about performance. We're going to define what a baseline is, how current activity can be compared with it. Everyone always wants to know how to make their maintenance tasks, databases, and resources perform optimally. We will take a closer look at that and even identify some of the major causes of performance issues. This is the first of two modules related to performance. Here we will compare Azure and on-premises tools for monitoring and measuring performance. We'll determine critical metrics and see the purpose of a baseline for a comparative analysis. Lastly, we will enlist and configure extended events and Azure Intelligent Insights for tracing activities. A baseline is a collection of metric data that helps you understand the normal, steady state of your application or server's performance. It's what normal resource consumption in your environment looks like. Discovering your baseline, or what normal in your environment is, will help us to determine what is abnormal in your environment or an anomaly performance-wise. We usually do this by having this data collected over time to identify changes from normal state. Most of this data is collected by default in Azure. Baselines can be as simple as a chart of CPU utilization over time or complex aggregations of metrics to offer regular, granular level performance data from specific application calls. The granularity of your baseline will depend on the performance of your database and application. As we will see, the metrics can be as simple as CPU and disk utilization, or we can collect a detailed set of metrics on our operating system and database utilization. With any type of application workload, it is imperative to establish a working baseline. A baseline will help us identify if an ongoing issue should be considered within normal parameters or has exceeded given thresholds. Without a baseline, every issue encountered could be considered normal and therefore not require any additional intervention. Azure Monitor is just one example of a tool that allows you to build a baseline for system performance for a given system. Establishing a performance baseline helps distinguish between code inefficiencies and increased resource usage. It also enables proactive scaling by identifying when additional compute resources are needed as workloads grow. Here we see how Performance Monitor, or PerfMon, a built-in Windows Server tool, can be used for tracking SQL Server and system performance. Whether you're running SQL Server on-premises or SQL in an Azure VM, PerfMon provides granular performance data through specialized counters for both the OS and SQL Server. You can group counters to streamline analysis and export data for archiving or deeper investigation, such as storing it in a SQL Server database. This enables administrators to monitor trends, identify bottlenecks, and make informed decisions about resource allocation and performance tuning. Performance Monitor, or PerfMon, is a foundational tool in Windows Server that many IT professionals have been using for over 30 years. It's easy to use, and it has been fine-tuned to help you analyze performance that can even be exported. Azure Monitor provides a centralized platform for tracking performance metrics across all Azure resources. When you deploy an Azure virtual machine from the Azure Marketplace, an agent is automatically installed that collects a baseline set of operating system metrics like CPU usage, network activity, and disk I/O, which are visualized in the Azure portal. These metrics are stored in Azure Log Analytics, a powerful repository that supports advanced querying using Custom Query Language or KQL. It's a SQL-like syntax that's been designed for efficient log analysis. Enhanced insights are available through Azure Monitoring Insights, which offer deeper visibility into your VM performance. This integrated monitoring approach enables proactive performance management, supports troubleshooting, and helps maintain system health across your cloud infrastructure. Azure Monitor metrics provide real-time insight into the health and performance of Azure resources by collecting metrics at regular intervals. These metrics can trigger alerts, either static, like CPU greater than 95%, or dynamic, based on learned behavior, which notify administrators or launch automated actions like Azure Functions or automation runbooks. Whether monitoring a single VM, a resource group, or an entire subscription, alerts can be scoped accordingly and sent via email, SMS, or integrated with your logical app. All metric data is stored in Azure Log Analytics, where it can be queried using the Custom Query Language and optionally archived to Azure Storage for long-term retention beyond the default 93-day window. Note that metric alerts can be defined on IaaS or PaaS resources. This system enables proactive issue resolution, performance optimization, and compliance monitoring across your Azure environment. Here we see how Azure Monitor tracks and analyzes performance metrics over time. By default, Azure Monitor retains metrics for 93 days, allowing users to easily review historical data using the date-time picker in the Azure portal. This feature is especially useful for identifying trends, diagnosing issues, and making informed decisions. For long-term analysis, users can archive metrics to Azure Storage, ensuring access to performance data well beyond the default retention period. This combination of short-term visibility and long-term archiving makes Azure Monitor a powerful tool for maintaining system health and supporting compliance and capacity planning. Here we see the essential performance counters and metrics for monitoring SQL Server on Azure Virtual Machine. Please note that you will need to correlate SQL Server behavior with the underlying operating system to help you to determine where the performance issue may be. Whether you're using Windows with Performance Monitor or Linux with tools like InfluxDB, Collected, and Gathana, these metrics help identify bottlenecks in hardware or code. For CPU health, percent processor time measures overall usage, while processor queue length shows thread contention, both useful for detecting CPU pressure and scaling needs. Memory-related metrics like paging file usage help identify when memory is being offloaded to disk, and page life expectancy reveals how efficiently SQL Server uses memory over time. Disk performance is tracked by using average disks per second read and write, which measure latency and help ensure storage is performing within optimal thresholds. For SQL Server activity, batch requests per second indicates workload throughput, and SQL compilation per second and recompilations per second highlight planned cache behavior, helping diagnose query inefficiencies or memory pressure. Extended events are a lightweight and very extensive diagnostic system that is built into SQL Server and Azure SQL Database and managed instance. Extended events allow you to collect additional information about the internal operations of your databases. Historically, DBAs used a tool called Profiler to trace inbound queries and gather execution plans to identify problematic queries and their execution plans. Extended Events builds on the functionality of the profiler by allowing you to trace queries and by exposing additional data or events that you can monitor. Some examples of issues you might troubleshoot with Extended Events include troubleshooting blocking and deadlock performance issues, identifying long-running queries, monitoring data definition language or DDL operations, logging missing column statistics, observing memory pressure in your database, and long-running physical I/O operations, and more. The Extended Event Framework also allows you to use filters to limit the amount of data you collect in order to reduce the overhead of data collection, and it allows you to more easily identify your performance problem by targeting your focus into specific areas. Extended Events in SQL Server provide comprehensive monitoring across the entire database engine, and it's organized into 4 distinct channels, each tailored to different diagnostic needs. The admin channel targets end users and administrators with actionable events like deadlock reports, helping quickly to identify and resolve specific issues. The operational channel supports diagnostics for common problems and can trigger automated actions, such as responding to an availability group failover. The analytical channel focuses on high-volume performance events, such as tracing stored procedures or query execution, offering deep insights for performance tuning. Lastly, the debug channel is reserved for advanced troubleshooting in collaboration with Microsoft support and may include undocumented events. Extended Events are grouped into sessions, which allow multiple related events to be captured together. This session-based approach enables focused monitoring of specific areas such as long-running queries, memory pressure, and I/O bottlenecks, while minimizing overhead targeted filtering. Here we walk through the process of setting up an Extended Event session in SQL Server Management Studio. This is a key tool for monitoring and diagnosing SQL Server performance. You can access this setup by expanding the management node in SSMS and then the Extended Nodes event right below it. You can then right-click on Sessions and select a new session. The wizard interface allows you to name your session, choose from a predefined template tailored to common monitoring scenarios, and configure options like tracking and startup behavior. For advanced users, sessions can also be created using T-SQL, offering greater customization. Extended Event sessions group related events together, enabling targeted diagnostics for issues such as deadlocks, long-running queries, or memory pressure, making this setup a powerful and flexible way to monitor SQL Server health. The slide titled here, Extended Events Components, illustrates how to configure an Extended Event session in SQL Server using the Management Studio, focusing on selecting relevant events and applying filters for targeted diagnostics. Events represent specific points of interest in the database engine, such as query execution or internal operations, and are added to a session to monitor activity. In the example shown, 3 events, SP statement completed, SQL batch completed, and SQL statement completed, are included to track completed statements. To refine data collection, a filter is applied to the field SQL.is system equals 0, which will ensure only users submitting queries will be captured. Also, it excludes system-level operations. This filtering capability is a powerful feature of Extended Events, allowing administrators to reduce the overhead and focus specifically on performance issues like blocking, deadlocks, long-running queries, memory pressure, and I/O bottlenecks. Sessions can host multiple events grouped to capture related activity and are created by navigating to the Management, Extended Events, and Sessions node inside the Management Studio and selecting, of course, New Session. T-SQL is the preferred way to create an extended events session due to its simplicity and repeatability. Event sessions can be scoped to a server or a database. In the example shown here, you are adding 2 events and using the event tracing for Windows path with a file location. After you create the session, you have to start it. You can do this using T-SQL and the alter session using the state option, or you can use the extended events session node in SQL Management Studio. You can also have the session start as a server startup, which is common for lightweight event sessions that you'd like to monitor over time. Here we see the steps for how to set up Database Watcher. This is a built-in Azure monitoring tool for Azure SQL Database and Managed Instance. The setup involves 5 key steps. The first step is search for Database Watchers in the Azure portal and click Create. Step 2, you choose your subscription, resource group, name, and region. Step 3, you configure the identity for authentication to the SQL Server targets, key vaults, and data store. Number 4, you set up the data store to collect monitoring data. And 5, you select the SQL targets you want to monitor. One of the key advantages of using Azure SQL products is their native monitoring capabilities. And Database Watcher exemplifies this by providing deep visibility into performance, configuration, and health across your SQL estate. It collects telemetry from databases, elastic pools, and managed instances, enabling proactive management without using external tools. Database Watcher leverages Azure workbooks to deliver rich dashboards at both the estate level and resource level. A featured example is CPU utilization heat map on the estate dashboard, where each hexagon represents a SQL target. The heat map visualizes 2 logical servers, one with 6 databases and another with 3, and includes high availability secondary replicas as separate targets. Users can interact with the dashboard to view more details, such as data ingestion statistics, making it a comprehensive and user-friendly monitoring solution. Here are some of the key capabilities of Query Performance Insights of Azure SQL Database's Query Performance Insight tool. It shows how DBAs can quickly identify expensive queries, drill into individual query details, and combine dashboard data with Query Store to pinpoint costly execution plans. These features make performance tuning more efficient and accessible. Traditionally, identifying resource-heavy queries in SQL Server required complex tracing and scripts, making the process really cumbersome. Azure SQL Database simplifies this with Query Performance Insights, and it's accessible from the intelligent performance selection of the database blade. It provides a visual, data-driven approach to performance analysis, helping administrators detect bottlenecks and optimize workloads with ease. When you launch Query Performance Insight, you'll discover 3 buttons to allow you to filter for long-running queries, top resource-consuming queries, or custom filters as shown at the top here. The default value is resource-consuming queries. This tab will show you the top 5 queries sorted by the particular resource that you select on the left. In this case, it was sorted by CPU. We also have other options of sorting by data I/O and log I/O metrics. You can drill into individual queries by clicking on the row within the lower grid. Each row will be identified with a unique color that correlates to the color within the bar graph above it. Now it's time for our knowledge check. Question 1. Which data store options can be used to analyze SQL monitoring data collected by Data Watcher? Answer: Azure Data Explorer. Question 2. Which extended events target only writes to memory and is not persisted? Answer: Ring Buffer. Question 3. Which performance monitor counter reflects how long SQL Server expects to retain data memory? Answer: Page life expectancy. Now let's take a look at how to isolate performance problems through monitoring. Hello and welcome to lab number 6. Isolate performance problems through monitoring is where we're at now. And in this lab, we're going to start off with doing some monitoring here inside of our Management Studio. So I have a few things already running. As you can see, what I have here is a query that's been running for about 15 minutes. It does run queries against our Azure AdventureWorks LT database. I got connected to that using my DP-300 Lab 1 database server, and it's been running for quite a while right now. It goes about 30,000 times against the database running our select statement here. Notice that the select statement has a counter, and it's going to iterate quite a number of times against it, and I can see a list here of all the times that it's gone through. And like I said, it's been running for about 15 minutes, so there's a lot of information here. This query is available in your lab, so you can copy it. It's suggested that you use it inside of Azure, but I found it a little handier to use here in the Management Studio. Getting connected to my Azure server and then accessing that AdventureWorks LT database. So it worked out pretty well here, and you can see a little bit of what it does, doing some joins, ordering, and just querying about 30,000 times, as you can tell. So what I'm going to do is I'm going to leave this running as I want to get some activity for our lab. I want to be able to isolate performance problems through monitoring. And I'm going to go into Azure, and I'm going to go back into Azure SQL. Remember, you can get that off the top if you need to by searching for it. And there inside of Azure SQL, I have this database right here that I'm going to run that query against. Now, the lab says you can do it here in the query editor, and you can come in here and you can log in with your account, and you just have to make certain that your account is actually enabled and it's ready to connect here. And I think I have done some changes and could continue with another account, so I could log in and do it right here. But there might be a little more that I have to set up right here, but it's kind of a limiting spot, I think. It's too limited. I like the Management Studio a little bit more. It gives us a little bit more flexibility. Plus, you have to turn on certain settings to get connected here. And what I'm going to do is I'm going to go out to metrics. Inside of metrics, what you're going to see is I have a little bit here of what's going on under the covers. And you can see some spikes here. Right there, you can see our query. So I ran it a couple times. One right there, and roughly it's been over 15 minutes. And now I may want to refresh that, and I can make other adjustments to it if I wanted to. I have the metric added here. I could add additional metrics. Maybe what I want to do is I want to add in this where I'm going to add a little bit more. I can add additional metrics to this if I'd like. And I might want to add in the I/O, the data I/O percentage there, and have that working also. So I can run a couple metrics at the same time. And once we get the information from the disk, and it'll be put into cache, and it's able to run the queries from cache, so it'll run faster. But you can see there's a little bump maybe when it first gets going, and I could add more if I'd like to kind of monitor some of the critical resources. But these are two critical areas here, and I could go through the metrics and look for a few more if I wanted to add in a few more to the list here. Deadlocks is a good option. I might have a lot of deadlocks going on behind the scenes here, so I could add that in. And I may also want to look at memory storage % here too. So I can look through and I can get a little bit more added to this so we can see specifically what's going on with this particular instance of SQL. It's memory. This gives us a little bit of, leeway here to see what else is out there if we'd like to pick something. One of the more common ones that it would be affected by. Now you can, with this metric view here, of course, I can change my chart. You can also go in and drill even deeper into some of these logs. Most of this information is being pulled up from our query store, but I could get into maybe one of my logs here, and I could do a little bit more of a deeper dive, see what's going on. This is showing me the top 5 queries by CPU consumption, and I'd have to actually drill a little further down into it to be able to get a little bit more data out of it. And there we can find, you can set up rules. There's some settings here that I can adjust if I'd like to get a little more granular with some of this, and even add this to the dashboard and then save it. Now this is showing me at 24 hours, so it's showing me that range. I'm going to narrow it down to the last 30 minutes and maybe get a little bit more detail there on what was launched and how it's been running. So it might be helpful. I could do a deeper dive into the intelligence platform off this blade system over here on the database and get into my query performance insights. So I can do that. From here currently, I may want to refresh and see if I can see any changes to this. The metrics gave us a little bit of a deeper look, but notice I'm looking at CPU. Notice its query aggregation is summed over the last 24 hours. I can customize this a bit if I want to do that. Maybe I want to make it a little bit more narrow over the last 6 hours. And I'm going to have it look at more than just the 5 queries it defaulted to, and give me a query aggregation average and also metrics aggregation average. And when I run this, we get, again, a little bit more detail in there. And if I keep scrolling down, you can see some of the queries that have been run, and they all have numbers and a query ID associated to them. Some of them have a little bit more. They run a little bit ago. I narrowed it down to the last 6 hours, and I'm going to pick this one up here, and it looks like the query we were running. So it took it within the last 6 hours. Here we ran this statement. We can refresh it. We can get into the settings. We can see what was run. We can see the duration that it's been running. And even if you can kind of see, it breaks it down into little intervals of when it ran, and how much CPU was used, data I/O, log I/O, the duration, the execution. All of this is very helpful. And you can see that you can focus on different options there. And if there's any recommendations, which there may or may not be at this point, you'd be able to see them right through here. So you have some way to get a little bit deeper into what's going on and narrowing down your selection. And so you can see resources consuming queries. You can see long running queries. So queries that have been running for quite a while, as you can tell from here. There's one that has 14,000 executions. So that's the one that I've been running for a bit. Here's another. I can break into it. And again, it looks like it takes us back to that same query now, that query that we've been running for a little bit here. And we're not able to get maybe as much detail here since it's mainly working with the query store, which focuses in this case, on select statements. So that's why we can't see the while command running right here. And I can keep it now, or I can drill further into it. I can go into Query Performance Insight. I'm going to go back into Performance Overview and see if I can get, I think I saw that screen before, so that our Performance Overview, we can also have that Performance Recommendations, and then we also have the Query Performance Insights, which is where we were, and you can get into a couple of different areas there to do a deeper dive on the queries, but automatic tuning can also happen. So automatic tuning is a very helpful option. This option is where we have it use a previous execution plan. If the current execution plan is becoming degraded over time, you know our performance is going down. We have to force the execution plan to a previous execution plan. Now it's inherited from the server, so it's currently turned on, and that server, of course, is our little DP-300 Lab 1 database server. It inherits from that, so it's turned on, and it will do it as needed. It also has turned on or turned off some of the options that are here, the create index, the drop index, and now we should let it, as it sees fit, be able to adjust these settings. Although sometimes people like to just turn it on right here. That way we have it right here instead of inherited from the server. I'm going to turn both of those on. I'm going to go ahead and save it, click OK. And now I have a little bit more control right here instead of just inheriting it from another setting. So I can set those on. And I can go ahead also and drop indexes that are not being used again, because it's going to enforce that when it sees fit. And then the plan, previous plan will be used in the event that we have performance degradation. So I can just tell it what to do right here. So inherit the plan from the server, or right here, create and drop indexes as needed. I hope you enjoyed this lab. And there's a lot more that we can dive into for monitoring. And we will do that in our next section. Welcome to our section on how to configure SQL Server resources for optimal performance. One of the challenges administrators face in the cloud is balancing costs with performance. Both Azure and SQL Server provide many options for configuration to meet the needs of small and large workloads. Choosing the right storage and sizing your virtual machine are critical steps in meeting the performance needs of your applications and balancing cloud costs. Proper configuration of SQL Server resources like TempDB, which can easily become a performance bottleneck, and Resource Governor, which can be used to manage multi-tenant workloads, are also important for properly maintaining your server's performance. Azure Storage offers 3 key storage types: blob, file, and disks. These are essential for supporting SQL Server workloads in Azure's scalable and secure environment. Blob storage is ideal for storing large amounts of unstructured data, making it perfect for database backups and archival scenarios. It also supports tiered storage options to optimize cost and performance. File storage provides fully managed file shares accessible via SMB protocol, which is especially useful for failover cluster instances and lift and shift migrations of legacy applications that rely on file shares. Disk storage offers high-performance block storage for Azure VMs, supporting mission-critical workloads with features like premium SSDs and zone-redundant storage for high availability. Storage performance is a critical component of I/O-heavy applications like database engines, and Azure's broad array of storage options can be tailored to meet specific workload requirements. All 3 storage types support encryption at rest, either using Microsoft Managed or Customer Managed keys, and ensure robust data protection across all scenarios. Azure Managed Disks offer 4 disk types: Ultra Disk, Premium SSD, Standard SSD, and Standard HDD. Each is tailored to different performance and cost needs for Azure VMs, especially SQL Server workloads. Ultra disks are designed for mission-critical databases offering configurable IOPS and throughput with extremely low latency, and it's ideal for high I/O workloads. Premium SSDs deliver high throughput and low latency, making them suitable for most transactional database applications that require consistent performance. Standard SSDs strike a balance between cost and performance, and they're best used for dev test environments or lightly used web servers needing predictable latency. Standard HDDs are the most cost-effective option recommended for infrequently accessed data like backups and archival storage. When migrating from on-prem, it's critical to capture performance metrics, such as average disk seconds read and write using Performance Monitor, and disk read and write I/O per seconds for SQL Server Resource Pool stats. Here we see how distributing data across multiple Azure disks without adding redundancy at the operating system level can significantly boost performance. Striping disks allows a volume to aggregate the IOPS and storage capacity of all included disks, which is particularly beneficial when using premium SSDs, as it helps to scale both throughput and volume to meet demanding SQL Server workloads, while Ultra disks offer flexibility to scale IOPS, throughput, and size independently on a single disk. Premium SSDs benefit from striping to achieve a similar performance gain. To implement this, you can use storage spaces in Windows, where you add multiple disks to a VM and create a pool without redundancy. Since Azure already provides built-in redundancy through synchronous replication of the 3 disk copies. For example, striping 10 P30 disks, each with 1 terabyte and 5,000 IOPS, results in a 10 terabyte volume with 50,000 IOPS. This is arrived at by adding each of the 10 disks 1 terabyte together to get the 10 terabytes, and then each of the 10 disks 5,000 IOPS together to get the 50,000 IOPS. Before migrating from an on-prem setup, it is recommended to capture performance metrics like average disk per second read and write from the Performance Monitor and disk read-write per second I/O for the SQL Server Resource Pool stats to understand peak IOPS, and gives us a better idea of how we need to design our Azure disk configuration accordingly. Let's look at some best practices for SQL Server storage. Here are some recommendations for optimizing storage performance and reliability in Azure-based SQL Server virtual machines. Consider planning an additional 20% of IOPS and throughput beyond baseline requirements to accommodate workload peaks and ensure consistent performance. One important best practice is to use the D drive, the locally attached SSD for your tempdb files, since tempdb is recreated on server restart and doesn't require persistent storage. This boosts performance without risking data loss. Additionally, it is advised to move trace files and error logs to a dedicated data disk to avoid contention with core database operations. For workloads that demand sub-millisecond latency, Ultra disks are recommended over premium SSDs due to their ability to independently scale IOPS, throughput, and size. These practices, combined with earlier strategies like disk striping, using storage spaces, helps to ensure that SQL Server VMs in Azure are both high-performing and resilient. The Azure SQL Virtual Machine Resource Provider simplifies and optimizes storage configuration for SQL Server virtual machines through its resource provider and deployment templates. Users can specify their required IOPS and data volume, and the resource provider will automatically allocate and configure the appropriate disks within the operating system. The configuration interface shown allows fine-tuning for storage for data, log, and tempdb files, including disk types, size, IOPS, throughput, and a number of disks. To reduce complexity, you can use SQL Server templates from the Azure Marketplace, which let you configure storage during deployment and automatically create storage space pools in Windows based on your IOPS needs. This streamlines setup and ensures performance alignment with workload demands. Additionally, the system can generate T-SQL statements to back up all databases on the server, which are typically executed using the stored procedure execute SQL or passed to external programs, making backup operations efficient and consistent. It is very important to properly configure tempdb to ensure optimal SQL Server performance. Tempdb is used extensively, and not just for user-defined temporary tables, but it's also used for internal operations like intermediate query results, sorting, and version stores. To support this heavy usage, we recommend placing tempdb on the lowest latency storage available, ideally the D drive on your Azure VM, which is locally attached SSD and safe for tempdb since it's recreated on every server restart. Best practices include configuring tempdb with the same number of data files as CPU cores, up to 8, and ensuring all files are equal in size and have identical auto-growth settings to avoid contention and maintain balanced performance. Prior to SQL Server 2016, DBAs often used trace flag 1118 and 1117 to address allocation and growth issues, but newer versions support these configurations natively. To simplify setup, you can use SQL Server templates from Azure Marketplace, which allows you to define IOP needs and automatically create storage spaces pools during deployment. Additionally, plan for 20% extra IOPS and throughput, again, to handle that workload peak, and move trace files and error logs to a separate data disk to reduce contention. For workloads needing sub-millisecond latency, Ultra disks are recommended over premium SSDs due to their superior performance. Here we see how SQL Server and Azure SQL Managed Instance use Resource Governor to manage and balance workloads with varying resource demands. Resource Governor enables administrators to segment workloads into resource pools, allowing control over CPU, memory, and IOPS for user sessions. These workloads are assigned using classifier functions, which evaluate session metadata and routes each session to the appropriate work group and resource pool. This is especially useful in a multi-tenant environment or servers hosting databases with multiple apps with different performance requirements and peak cycles. The diagram illustrates how sessions are classified and directed to either internal, default, or custom resource pools based on their characteristics of the user or app connecting. Resource Governor was introduced in SQL Server 2008, and it remains a very powerful tool for granular resource control. You can configure limits such as min and max CPU percentage, memory percent, IOPS per volume, and even NUMA node affinity. It helps ensure consistent performance across apps, and it can also be used to throttle resource-intensive maintenance tasks like index rebuilds. Now it's time for our knowledge check. Which type of storage should be used in conjunction with Azure VMs for SQL Server data files? Answer: disk storage. Question 2. Which of the following can be limited using Resource Governor? Answer: write IOPS. Question 3. Which is an option for the SQL Server resource provider for Azure VMs? Answer: storage configuration. In this section, we took a look at how to configure Azure storage, including how to configure tempdb data files in SQL. We also discussed how to choose the right type of VMs for different SQL Server workloads, and then showcased how you can use Resource Governor to configure resources for different server use cases. In this section, we're going to get very specific and start talking about how to configure databases for optimal performance. In recent versions of SQL Server, Microsoft has moved from configuration options to database level, giving you more granularity in how your databases behave. Along with those options, they have introduced features as part of the intelligent query processing that allow the database optimizer to make better choices when it generates query execution plans. Here are 4 essential tasks. Database backups, which protect against data loss and support recovery in disaster scenarios. Consistency checks, like DBC CheckDB, which scan the entire database for corruption and are typically scheduled during off-peak hours due to their I/O intensity. Index maintenance, which improves query performance by reorganizing or rebuilding fragmented indexes, often done weekly. And statistics updates, which refresh optimizer data to ensure efficient query execution after significant data changes. These tasks are often automated using maintenance plans, built as integration service packages, or managed with open source scripts for greater flexibility. In production environments, these operations are commonly spread throughout the week to balance performance and uptime requirements. SQL Server maintenance activities, backups, consistency checks, index maintenance, and statistic updates help ensure data integrity, optimize performance, and support reliable query execution, especially in our production environments. Here we see how fragmentation occurs in SQL Server when inserts, updates, and deletes cause index pages to split, disrupting the logical to physical order of data and degrading query performance, especially for scan operations that require more I/O. Fragmentation is common in both clustered and non-clustered indexes and can be mitigated by reorganizing or rebuilding indexes, which restore order and improve efficiency. Additionally, adjusting the fill factor of indexes allows space for future inserts and updates, reducing the likelihood of page splits. Index reorganization reorders the leaf level of pages in an index to reduce fragmentation without fully rebuilding it, offering a lightweight option ideal for moderately fragmented indexes during regular maintenance. Index rebuilding recreates the entire index structure, eliminating all fragmentation and improving performance for heavily fragmented indexes, especially in high transaction environments or during scheduled maintenance windows. These maintenance actions are particularly beneficial in high transaction environments where performance consistency is critical, and they help ensure faster query execution and better resource utilization. Index maintenance tasks are a critical role in optimizing database performance. It emphasizes that SQL Server and Azure SQL support resumable and online index operations, allowing maintenance without disrupting workloads. Indexes should be reorganized when fragmentation exceeds 5% but is below 30%, and rebuilt when it surpasses 30%. Though this guidance should be adapted based on workload and data volatility. Beyond proper indexing, maintaining healthy indexes and up-to-date statistics enables the query optimizer to generate more efficient execution plans, especially for scan-heavy queries. This ensures faster query response times, better resource utilization, and sustained performance for data as it evolves, making index maintenance a foundational practice for reliable and scalable database systems. Here we see two key maintenance operations in SQL Server: reorganize and rebuild. Reorganize is a lightweight online operation that physically reorders the leaf-level pages of an index to match the logical order, helping to reduce fragmentation. It also compacts pages based on your fill factor setting. This method is ideal for moderate fragmentation and minimal system impact. It improves performance with minimal system impact by reordering the leaf-level pages and compacting them online. Rebuild is a more intensive operation that drops and recreates the index pages, updating statistics in this process. It can be performed online or offline, and it is recommended when fragmentation exceeds 30%. This approach ensures optimal performance, but may require more resources. Rebuild is suited for heavily fragmented indexes above 30% or when updated statistics are needed. The alter index all command applies a specified maintenance operation such as reorganize or rebuild to all indexes on a given table or view, helping optimize performance and manage fragmentation efficiently. Index maintenance tasks can be effectively automated in SQL Server environments, especially when installed within an Azure virtual machine. By leveraging built-in scheduling, tools like our SQL Server agent and the Windows Task Scheduler, administrators can automate routine tasks such as reorganizing indexes when fragmentation is between 5% and 30% and rebuilding them when it exceeds 30%. Ensuring optimal performance without manual intervention. This flexibility is particularly beneficial for larger databases where balancing between reorganization and rebuilding operations is crucial to maintain efficiency. Organizations migrating from on-prem setups can also continue using familiar maintenance workflows, and the ability to run custom jobs through SQL Agent or Task Scheduler allows tailored solutions that keep index fragmentation to a minimum and support consistent, high-performing database operations. Although Azure automatically manages tasks like consistency checks and backups, DBAs are still responsible for maintaining indexes and statistics to ensure optimal query performance. Unlike traditional SQL Server environments, Azure SQL Database does not provide access to SQL Server Agent or Windows Task Scheduler, which are commonly used for automating index maintenance tasks like reorganizing or rebuilding indexes based on fragmentation levels. Instead, DBAs must rely on external scheduling solutions like Azure Automation Runbooks, Azure SQL Elastic Jobs, or SQL Agent Jobs from SQL Server running in an Azure virtual machine to automate these operations. These tools allow DBAs to maintain performance and data integrity by keeping fragmentation low and statistics up to date. especially in large or dynamic databases. The flexibility of these external options ensures that maintenance can be tailored to workload patterns and business requirements, even in cloud-native environments where traditional scheduling tools are unavailable. Index maintenance tasks on Azure SQL Managed Instance highlights how Azure SQL Managed Instance supports built-in automation for index maintenance through the inclusion of our SQL Server agent and the MSDB database. This is similar to on-prem SQL servers or Azure VMs. This enables database administrators to schedule jobs that reduce index fragmentation and optimize query performance over time. While tasks requiring file system access must be modified due to platform limitations, the ability to automate routine operations such as index reorganizations, rebuilds, backups, and integrity checks offers significant benefits. This includes reduced manual effort, improved consistency, and enhanced database efficiency. As with SQL Server on an Azure virtual machine, scheduling jobs via SQL Server agent on the Azure Managed Instance provides flexibility to execute targeted maintenance scripts, ensuring indexes remain healthy and performance remains high in dynamic workloads. SQL Server relies on statistics from columns and indexes to build efficient execution plans, making it essential to keep these statistics up to date for all database objects. SQL Server simplifies this process by enabling auto-update statistics by default, which reduces manual intervention and ensures performance remains optimal as data changes. The engine uses a sliding scale to determine when enough modifications have occurred to trigger a statistics update, allowing dynamic responsiveness to workload changes. This approach benefits high transaction environments and large-scale databases by maintaining query performance and minimizing the need for manual tuning, making it ideal for DBAs seeking consistent and efficient database operations. Here we see an outline of how SQL Server databases can be fine-tuned using two types of settings, those configured via Altered Database Scope configuration and those via Altered Database Set. These options, such as recovery model, isolation level, automatic tuning, and intelligent query processing, are set at the database level and often depend on the database's compatibility level, which itself is a configurable setting, as you know. While the method of configuration differs, both types of options serve the same purpose, enabling administrators to optimize performance and behavior for specific workloads. Use the Altered Database Scope configuration when you want to fine-tune performance-related behaviors specific to a single database, and use Altered Database Set for broader database settings like recovery model or compatibility level. Both methods serve similar purposes, and the choice depends on the type of option being configured rather than any functional difference. Benefits include enhanced query performance, better resource management, and the ability to tailor database operations to application needs. Use cases range from tuning transactional systems for faster response times to enabling advanced features in analytical workloads, all while maintaining backward compatibility with older SQL systems. In automatic tuning, SQL Server and Azure SQL Database use the query store to detect and respond to performance regressions caused by sudden changes in query execution plans. Once enabled, automatic tuning can force a recommended plan when the previous plan has more errors. The estimated CPU gain exceeds 10 seconds, or a previously forced plan continues to outperform alternatives. The force plan underperforms after 15 executions. The engine reverts to the last known good plan and continues monitoring performance. This cycle of learning, adapting, and verifying ensures sustained query efficiency. Benefits include reduced manual intervention, faster recovery from performance issues, and consistent optimization across workloads. Use cases for this include high transaction environments, dynamic workloads, and systems requiring reliable query performance without constant DBA oversight, which might be most of our databases. Automatic index management in Azure SQL Database is a feature that intelligently analyzes workload patterns to optimize performance by automatically creating and dropping indexes and forcing improved query execution plans when regressions occur. Once enabled, the database engine monitors query performance and can force a recommended plan if the previous one fails or has a significantly higher estimated CPU cost. It will revert to the last known good plan after 15 executions that performed under what we wanted it to do. If they've underperformed in that, it'll force the plan on it. Over time, Azure SQL Database learns from workload behavior and provides recommendations or takes action to maintain efficient indexing, reducing fragmentation, and improving query response times. Benefits include reduced manual tuning, consistent performance, and adaptability to changing workloads, making it ideal for dynamic applications or environments with limited DBA oversight. Use cases here are for high transaction systems, SaaS platforms, and cloud-native apps where automated performance tuning usually ensures reliability and scalability. Automatic plan correction in SQL Server is a feature that monitors query performance and automatically forces the last known good execution plan when regressions are detected, such as when the previous plan has more errors, the estimated CPU gain exceeds 10 seconds, or a previously forced plan continues to outperform the prior one. If the forced plan no longer performs better, SQL Server will unforce it and compile a new one, ensuring continuous optimization. This behavior is tracked and recommended through that dynamic management view, sys.dm DB tuning recommendations, which helps DBAs evaluate and apply tuning suggestions. The command set automatic tuning force last good plan equals on will enable SQL Server to automatically revert to a previously successful execution plan when a newly compiled plan causes performance degradation, improving query efficiency and reducing manual tuning in a dynamic load. So there's a lot of benefits with this, with query performance. There's reduced manual intervention, and this will help us to minimize the downtime due to our inefficient plan. And this can be used in a lot of different scenarios, dynamic workloads, mission-critical apps, and environments where consistent query efficiency is essential. Intelligent query processing is a suite of features in SQL Server and Azure SQL Database that enhance query performance and resource efficiency by enabling the database engine to make smarter execution decisions. These features, such as adaptive query processing, approximate query processing, and query processing feedback, automatically optimize queries through mechanisms like adaptive joins, memory grant feedback, and scalar UDF inlining. A major benefit is that most of these enhancements require no code changes, allowing existing applications to benefit immediately. They also help correct common anti-patterns like user-defined scalar functions and table variables, which traditionally hinder performance. Use cases include improving execution plans for complex queries in large-scale databases, reducing manual tuning, and ensuring consistent performance for our databases. Now it's time for our knowledge check. Which intelligent query processing feature allows for fast calculations at a large number of rows? Answer: batch mode on row store. Question 2. Which component of Resource Governor allows you to configure limits on system resources? Answer: resource pools. Question 3. You need to migrate a set of databases that use distributed transactions from your on-prem SQL Server. Which of the following options should you choose? Answer: Azure SQL Managed Instance. Now let's see how to detect and correct fragmentation issues. So join me in Lab 7, Detect and Correct Fragmentation Issues. And this lab kicks off in our Management Studio. So what I've done already is I have restored our AdventureWorks 2017 file. Right here. This is a typical file that you can download as a sample file from the AdventureWorks website. It also is a lab file, so you should be able to get access to it. And I've restored it, so I'm going to show you here in the list. Here is a refresh so that we can see it right here. There it is on the right. And as we get into this query, I'm going to go ahead and I'm going to do a new query. And I'm going to go ahead and paste in the index fragmentation query that that will just check that database, and I'll see if maybe there's any fragmentation in it right now. There shouldn't be any fragmentation in it right now because this came right from the factory. So not a lot of changes to it. But if we do add changes, which I'm going to do here in our database, I'm going to insert a lot of records. I'm going to delete records. I'm also going to insert about 10,000 records and delete about 25,000 records. So actually, 60,000 records I'm going to work with here and 40,000 records for the insert. So this is actually going to cause some fragmentation, which we can then see that we'll get bad performance from when we start querying it. So we've added in and removed a ton of records. There's been a lot of movement. And I'm going to go back to the query we ran previously and see if there's any fragmentation. Notice it's 10% fragmented. And we're going to execute this one more time. And yeah, you're going to see a lot of fragmentation on a number of our indexes, the address line to the city state. So some fragmentation there with the state. There's one or more of these indexes that are really fragmented, as you can see. So what we might want to do is we might want to take this a step further here and do some statistics I/O. Now the statistics I/O will give us a little bit of an idea what's going on with our system right now. What we want to do is go ahead and run this query against the address table and see what kind of performance we get from it with our fragmentation. So when we talk about fragmentation, fragmentation is really bad for queries. And this is a query against a fragmented address table there. Now it looks as though it executed in about 2 seconds to give us 125 records. But if we go into messages, what do we see here? When messages, we can see a little bit more info about this elapsed time. Here's server parsed and compiled. How many milliseconds? It took it a lot of milliseconds, but this can really compound over a ton of time. So this is a very small table, but over time it can build up and give us even worse performance. Notice that we have about 290 logical reads. So what it did was it read through the address table and it got that information, and then it read it logically into memory. And each page is about 8K in size, and it's having to parse 290 pages to do that. So we're getting a lot of memory use out of this. So it isn't bad, but over time this could get a lot worse, especially as we do more inserts, updates, and deletes. And in milliseconds, here our execution time. So it's giving us a good look here at what's going on. And what we might want to do is we might want to work with rebuilding our index. Remember, if we go above 30%, we want to do a rebuild. So that's what we're going to do. And we're going to try to do our rebuild here. And we're going to rebuild that one table. And there are multiple tables that are actually had high fragmentation, but this one is going to be just the one we're going to use right now, rebuild and analyze and get a closer look at what it looks like. So now we're going to run another statement here, and this is going to give us another look at one of our other tables and see how fast that runs. And looking at index fragmentation again. And so we execute this one more time. Notice we got our fragmentation down to 0. So that works out really, really well for our address table. We rebuilt that one. The index fragmentation has gone down to 1. And then we're going to take a closer look here and looking at the statistics IO and see if we can reduce the statistics IO here too. So we're going to execute this here. And now we see our statistics IO is a lot faster. 125 records that were turned in less than 1 second. And you can see our logical reads are now down to 166. So we reduced it quite a lot. So this can be very helpful to make certain that our queries run as fast as possible. There's always a lot of movement in these tables, inserts, updates, deletes, and so our queries over time can run slower because of that. But we have a really good lab here that will kind of give us a little bit of a look at how this can impact our indexes. And we had to rebuild one of our indexes, but there's other indexes out there too that we can work with for performance. And we may want to go and rebuild some of those other indexes too. So we had a number of them out there. And I think this one right here, yeah, this was a couple that was really slow that we may want to rebuild. So we're going to take a look at the list and see which ones we might want to rebuild. So hopefully this helps showing you the kind of impact there is when you rebuild indexes and the impact that it has on your query performance. Thank you so much, and I hope to see you in the next section. For more information, please check out our overview of Azure Monitor, our monitoring performance by using the Query Store, and our overview of extended events and intelligent query processing. In this section, we explored key strategies for boosting SQL performance, starting with monitoring tools like Azure SQL Insights and critical metrics to spot issues early. We then optimized SQL Server resources, configuring Azure storage, TempDB files, and Resource Governor for peak efficiency. Finally, we turned our databases with scoped options, automated index and statistic maintenance, and enabled auto-tuning in Azure for smarter, hands-off performance gains. Thank you for your time and attention in this optimization section. I look forward to seeing you in the next.